Module 1 in DSP has few contents, and it is easy also compared to all other modules. First module is consists of mainly signals. It consists of signals. We have already discussed about this, and in this signals we have types of signals. Types of signals we have, and we classifications, we call this as classifications, and initially we have a definition of this, and then after this types, actually there are plenty of types of signals. Among that, your analog signal, analog and digital signal, continuous and discrete signal, and discrete signals. Then we have power signal, energy signal, and periodic, non-periodic, random signals, non-random signals, and definite signals, and so on. So after this classifications, we have basic actually we have to go ahead with the basic operations. Basic operation. So these initially is basically means two. One is with respect to x-axis and another one is with respect to y-axis. With respect to our y-axis we have, with respect to our y-axis we have amplitude, amplitude, the amplitude, and then we have, it's also called as a scalar, scalar, and along with this we have addition, subtraction. So 5k amplitude multiplication also you can call amplitude, scalar. It's nothing but the signal which is going to be varied with respect to y-axis. That is your scalar quantity also you can call, right? So with respect to y, amplitude you can call, scalar you can call, you can have addition, you can have, and then multiplication we can have. Then these are all our y-axis operations, and another comes x-axis operations. X-axis operations means with respect to your x-axis with respect to your time. Time. So in this time we have two types. One is shifting, another one is we have scaling. Shifting we have and a scaling we have. Shifting means like this, t plus 1 or t minus 1. These are all our shiftings. T minus 1 indicates t is equal to 1. Our signal starts from 1. So this is plus 1. T plus 1 means t is equal to minus 1, where your signal starts from minus 1. Like this. It may be continuous or it may be discrete. Whereas your scaling, actually with respect to time, indicates like this, t by 2 or 2t. For example, u of 2t indicates u of t is this. This is the signal which has from 0 to t we have one magnitude, right? This is u of t. What is u of 2t? U of 2t is 2t we have to take, 2t is equal to 1, t is equal to 1 by 2. Therefore, your u of t, whatever we have u of t, its magnitude remains the same. But timing, it will be t equal to 0, 0 to t. Then it will be starts from 0 to t by 2. T is going to be changed by 1 by 2. So suppose u of t by 2, then your signal will be t by 2 equal to 1, then t is equal to 2. So your signal will be from 0 to 2t. In this way. So this is about your basic operation on the signals. This is with respect to y-axis and this is with respect to x-axis. This one we have, and along with this we have signals properties. Signal properties, and remember properties in all the modules are very important. So for your syllabus, properties of in the first module we have properties of the systems, and in the first module only, second part, which is time domain LTI, time domain representation of LTI system, linear time invariant systems. There also you have properties of impulse response. Okay, properties of impulse response. And then in the second module we have a DFT, properties of DFT. So properties are important for us to study purpose for the examination. Okay, properties of a systems, properties of LTI system, properties of DFT. Okay, so along with these properties, there will be many questions on this, right? So simply explain the properties, or write the properties of the systems, explain the properties of LTI, or write the properties of DFT. Okay, in this way these will be. And after this, in module 1, after this properties of the systems, we have a concept of a frequency, continuous and discrete time signals. Okay, how to express in frequency domain, that we have. And then after that, sampling we have. Okay, sampling of analog signals, and sampling theorems. Okay, Nyquist theorem, and over frequency theorem, and under frequency. Okay, these theorems we have. After this, quantization of continuous amplitude and sinusoidal signals. Okay, these we can study in module 1, which is first part. Okay, so in the meanwhile, in the second part of the module 1, we have a time domain representation of LTI system, where it includes convolution mainly. Okay, convolutions. So right, so simple convolution, and we have convolutions, linear convolution, then circular convolution, and in this only we have its solutions also with respect to this linear and convolution, right? And again we have impulse response representation, impulse response representation. And remember, in the convolution, in the convolution, continuous signals are we have infinite signals, actually not continuous, we can say infinite signals are have a definite convolution. So you can have only 3 conditions: less than 0. Okay, we can have a less than 0, and at 0, and then we have greater than 0 condition. So these 3 condition only we get it in infinite signals. Whereas in finite signals we have all the cases, these are, since finite signals has a definite intervals, starting point and end point, so there we have a more convolutions chances. Okay, this is about your first module. First module is the second part as well. As I said, properties we have to study, properties of impulse responses and solution of difference equations. Okay, and next we'll have a second module, which is completely on DFT. Okay, second module is completely on DFT. Okay, discrete Fourier transform. We have a formula for this, summation of, that is x of k is equal to summation of n is equal to 0 to n minus 1 x of n into e raised to minus j 2 pi by n into nk. Okay, so this formula we have, all the problems will be related to with respect to this only. Here in this we can find the DFT and find the magnitude and spectra of that sequence, magnitude, spectra and phase angle also. And next we have IDFT as well, inverse discrete Fourier transform, whereas x of k will be known and we have to calculate x of n. After this, properties again, properties. So mainly in all the properties we have a linear property. Okay, all the properties, linear properties and So what is this? Linearity, circular time shift, especially in DFT we have a circular time shift, and circular folding, sequence multiplications, and real and odd sequences. Okay, these are all the properties of DFT. This we have to study. And after this DFT, even Parsel's theorem was also there in the properties only. And after this we have overlap save and overlap add method. Overlap add and overlap save method. So after this, third model is very easy. You can concentrate if you know the technique behind that. FFT, we always try to prove that FFT is better than DFT. So FFT is mainly in this we are going to find out the DFT and IDFT. Okay, so DFT we are going to find out by two methods. One is okay, so for all these things FFT we are using radix 2 FFT. Okay, radix 2 algorithm. Okay, radix 2 algorithm we are using. In this we are finding out DFT. One is in that DFT we have two methods using radix 2 algorithm. One is DIT FFT to find out the DFT, and another one is DIF FFT to find the DFT. Okay, DIT is a decimation in time, whereas DIF is a decimation in frequency. Similarly, IDFT also we have two types. One is DIT FFT, that is IFFT, okay, to calculate IDFT, and another one is DIF FFT, okay, IFFT, which is to calculate IDFT. So these are the things which we are going to study in module 3. All right. So along with this comparison of your efficiency, why we have to prefer FFT. So for that I have explained in the previous video while solving the numerical on endpoint DFT, where the calculation, addition, summation, we can call it as addition or subtraction, summation and multiplication. Number of summations and number of multiplications carried out in DFT are more as compared to your FFT. That's what we prefer FFT. Okay. And come to fourth module. It is completely of your IIR filters. And in this IIR filters you have mainly two types of filters. One is Chebyshev and another one is Butterworth filter. Okay, we have to study first design of this, and in Chebyshev we have to find out the polynomials as well. Only thing is right now to spend on this one is not a good idea, since you have exam tomorrow itself, right? Designing and design of both the filters and polynomial of Chebyshev filter is easy, but thing is concept supposed to be understood earlier only. This is design of IIR filter. Okay, along with this, in this IIR filter and IIR filters, Chebyshev and Butterworth comparison, they will ask what is the compare Chebyshev and Butterworth. Remember, Butterworth is, as name itself indicates, it is very smooth in nature. Okay, buttery in nature, whereas Chebyshev has spikes. Okay, so this generally I explained, but technically there are many changes in these things. Okay, so comparison of Chebyshev and Butterworth filters you can have, and after this there is a representation actually. So these are like design of this Butterworth and Chebyshev filters using bilinear transformation, that is called as BLT, bilinear transformation, and impulse invariance technique, that is IIT. BLT and IIT, design of Butterworth and Chebyshev by BLT and IIT. These two are definite procedure. You can easily tackle this. Even if you wish, I'll make a I'll prepare this and then I'll hand over to you. Okay. BLT and IIT methods to design this Butterworth and Chebyshev. So these two methods are very easy. It means definite one. BLT method, bilinear transformation method, and impulse invariance technique. These two are like an easy one, fixed one, like fixed type. There is a procedure. If you follow, like you can complete the task. And along with this BLT and IIT, you have a representation which we have already discussed. Representation of IIR filters. So IIR filters representation is nothing but your realization also. Realization which I took. Okay, realization of IIR filters. In that we have series and parallel form. Okay, so series is nothing but your cascade form and parallel form. Similarly for model 5 is actually model 5 is a quite easy one compared to all others one, because it is FIR filter design. Okay, FIR filter design. So in this windows we have to study mainly. Windows, there are mainly 4 types we are going to study, windows are rectangular window, and Bartlett, Hamming and Hanning window, and Blackman windows. Okay, these windows, there are actually what we have to remember in this is formulas of all the windows. Rectangular windows formula, and Blackman's windows formula. Okay, fixed one. This nothing is going to change in this. Rectangular window, Blackman's window, and then Hamming and Hanning windows. Okay, Hamming windows and Hanning windows. So their formulas we have to remember. Okay, if we remember these formulas, easily we can tackle this. It is very easy. Only thing is to remember the formulas. Okay, so design of different differentiators and Hilbert transforms. So this is how we have studied in Chebyshev and Butterworth, like BLT and IIT. Here also we have to study different differentiators and Hilbert's transforms. So these two we have to study. And then we have sampling techniques for frequency representation. This is one topic. And last we have representation, which is nothing but your realization of FIR filters. In this we have direct form and lattice structure. Okay, lattice structure. So these things you can concentrate.